Okay, the photoelectric effect. This is probably one of the bigger topics of this lecture, and it's mostly because it's going to rely on also unit conversions, which we'll talk about soon enough. All right, photoelectric effect. What basically happens in this premise is that you have a metal surface and you shine light. Now, according to classical physics, it didn't really matter what the frequency or the wavelength of the light were. What would matter is that you actually shine the light either long enough or with high enough intensity such that continuously you will provide enough energy to remove an electron from the metal. And surprisingly to them was the fact that that didn't pan out. You could actually use light of, let's say, low frequency or long wavelength, and it didn't matter how long you exposed the metal surface to that light or how high the intensity of that light was or how long and how intense the light was, no electrons will come out of it. And unless you hit a very specific value for the frequency or even higher than that specific value, that threshold value, no electrons will come out. But the moment you use light of a very threshold frequency value, you will then get electrons coming out of it. And at that point, if you increase the intensity, you will get even more electrons coming out of it. But unless the frequency was of that value, you will get no electrons. And this kind of fly in the face of physicists thinking that energy was just continuous. You could just continuously provide the energy inputs and get higher and higher and higher and higher quantities of energy provided to the metal. But that wasn't the case. Unless you had a specific frequency, you would not get an electron out of it. So it looks like the amplitude actually had nothing to do with the energy of the wave. And it looks like the frequency may actually be at play. All right, so the photoelectric effect, this actually has an equation associated with it that has not only historical significance, but this is, in fact, one of the experiments that Einstein himself worked on back in the early 1900s. And most people actually have the erroneous idea that Einstein won the Nobel Prize for his work on relativity, but it turns out that he never won the Nobel Prize for relativity. He actually won it for performing the photoelectric effect and coming out with the result that I'm about to discuss. All right, so if we think about what's going on here, you shine light on a metal surface, and if you have the right frequency, you get electrons coming out of it with some kinetic energy. Pretty much the light source shining onto the metal is the total amount of energy provided to the metal surface itself. The electron coming out of the metal has some kinetic energy associated with it. And kinetic energy plus potential energy always have to equal the total energy of the system. Now you may ask, well, kinetic energy is the electron coming out of the metal, and the total energy is the energy of the light being shined on the metal surface. So what is the potential energy? And the potential energy is nothing more than the attraction of the electron to the nucleus of the metal, whatever metal this is that attraction, the electron to nucleus attraction, that you're trying to basically compensate the atom for as the inconvenience of removing an electron from it in the first place. So the potential energy has a few terms that you need to be familiar with. Potential energy is one way to refer to it. Another way is to refer to it as the work function, which uses the symbol phi. And another way to refer to it is as the ionization energy of the metal. So all three of those things are the same thing, potential energy. All right, so the kinetic energy of the electron is and can be determined simply by subtracting the potential energy of the metal from the total energy. And pretty much what happens was that Einstein, when he did this experiment, looked at just that. He looked at the kinetic energy of the electron as they were being removed from the metal, and he collected that data as a function of the frequency of light being used to shine onto the metal. And what he basically found out is that the kinetic energy of that electron had a complete linear correlation to the frequency of light being used. And so when you plot this line, you get a linear fit, which gives you the equation 6.626 times 10 to the negative 34 multiplied by the value of x, which is the frequency. And here's what I was kind of referring to earlier on. The frequency has the symbol mu. This is not v, but rather mu, the Greek letter, minus, okay, some value, right? And the 6.626 times 10 to the negative 34 is Planck's constant. So this is actually rather intriguing because Einstein is doing an experiment involving the removal of electrons from a metal source. And Planck did an experiment where he was basically trying to explain how heating up an opaque solid generates light of a given energy. And from those two experiments that seem to have to do nothing with each other, Planck's constant just comes out naturally out of the relationships. And it's basically this point that it becomes obvious that Planck's constant is just not just some nuisance, just some peculiarity of an experiment, but it's rather a natural constant of nature that permeates throughout the world of quantum mechanics. So pretty much what we're seeing here is that, okay, kinetic energy is the y, and then we have the frequency on the x, but we know that kinetic energy equals total energy minus potential energy. So if the slope, which is Planck's constant, times the frequency has to equal the total energy, then that means that the potential energy, which is equal to this value here, has to also equate to Planck's constant times the base value, the threshold value of frequency, which is necessary to remove the electron in the first place. So the beauty of this process is that we basically are able to tell what minimum frequency needs to be achieved in order for you to have electrons coming out with kinetic energy of any sort. This particular value, the V naught or the nu naught, is what we call the work function of the metal. We also refer to H mu naught as the ionization energy of the metal or the potential energy associated with it. Okay, but this basically sets up, yes, and of course, if you extrapolate and say that H times mu naught equals the y-intercept, then mu naught ends up yielding a value of 9.911 times 10 to the 14 hertz. Altogether, however, what this basically says, aside from the fact that energy is discrete and you need to hit that right value of energy for the electron to come off in the first place, is that we now have a representation for energy in terms of frequency, and amplitude doesn't even make an appearance in this equation. It's all about the frequency. The frequency of the light multiplied by Planck's constant, 6.626 times 10 to the negative 34 joules times second, is equal to the energy of the light source. And since frequency times wavelength equals the speed of light, we can rewrite Planck's equation by saying that frequency equals the speed of light divided by wavelength, meaning that the energy itself can be given by Planck's constant times the speed of light divided by the wavelength. One thing that needs to be said though is that in the context of these equations, the frequency has to be in hertz or per second, and the wavelength has to be in meters, not nanometers, not micrometers, but meters itself. I will be doing some calculations in the next video where I'll depict those particular setups. But the two aspects of this video that need to be accounted for are these three equations. Total energy equals kinetic plus potential energy. We're actually going to use the photoelectric effect for that. Specifically, the total energy is the energy of the light source. The kinetic energy is the energy of the electrons coming out of the metal. And the potential energy is the same thing as ionization energy or work function, and relates to the attraction of the electron to the nucleus of the metal itself. Aside from that, we have two versions of Planck's equation that tell you that energy is correlated to the frequency and is correlated to the wavelength of the light. Alright, so with that, the last thing to be said is that with these two experiments, the photoelectric effect and the black body radiation, ultimately Planck and Einstein, among other scientists, showed that light actually comes in discrete packets of energy. Discrete packets of energy are also referred as quanta, which is where the name quantum mechanics comes from. Now, these discrete packets of energy are called photons, and this is something we're going to touch upon a little bit later in this lecture, But the idea that light comes in discrete packets is kind of presenting and setting up the picture that light might actually be behaving like a particle and not so much as a wave. This is something we're going to investigate a little bit more in future videos. Okay? So, and lastly, amplitude or intensity of light basically just tells you how many photons you're going to have, but it doesn't actually change the energy of the light. The energy of the light is completely and directly related to the frequency of the light. Okay, so with that, we're going to stop the video right here and we'll continue on the next one.